Hey, as I warned you, we are entering very mathematically heavy slides, but don't worry, you don't need to uh, read most of them, so I will really quickly go through those pages. So we'll skip everything. So maybe if you want, you may want to keep this in mind, but still does not matter. It is about how we calculate beta 1 hat. So beta 1 hat is calculated this way, but it is not important because the Stata, the program, is going to calculate this for you. So you will never use the formula itself unless you do some proof or derivation by hand. So it's automatically calculated by the program. And after some complicated derivations, you get to this point. The point of this, what it means is, this is important because beta hat is your estimator, and beta 1 hat is your estimator, and beta 1 is the true value. So you would like to estimate beta 1, and you estimate it by beta 1 hat. So their difference is the estimation error in your estimator. So, and as I said, basically we would like to study the distribution of the estimation error, and this is what it is. This is what we would like to analyze. We would like to examine how it is distributed. And on the right hand side, what you can see here is there is a denominator and numerator. So x is like student to teacher ratio. So that does not cause much problem. The problem is from this error term, u. U is, I will call the error term, I will assume that the error term is the randomized difficulty of the test to make it easy. So depending on how random, how uncertain the difficulty is, then your estimation error will be determined. For example, suppose that the test is really nicely designed, so even after a lot of randomizations, the difficulty does not vary much, does not vary at all across different testing places or testing locations, times, then the error term will have small amount of noise, so your estimation will be very accurate. If not, so suppose that the error is large. Sometimes it's too large, sometimes it's too negatively large. So the difficulty of the test is not stable. Sometimes too high, sometimes too low, too easy, too difficult. And then there it means that there is a lot of noise in the underlying data. So automatically your estimation error will be large. So that's how it is, what we are going to get in later. Just it is proved mathematically, and that is that appears here at a term. And then first, we would like to calculate the mean of the estimator. Mean, the average of the sample mean, estimation error. The estimation error, if you take expectation, so if you take expectation on this guy, then what we need here is, the key assumption we need is this: no matter what x is, your error term is always expectedly 0, right? So we discussed this assumption earlier. So no matter what your student to teacher ratio is, the difficulty is anyhow random. So expectedly there is no problem. Your difficulty is on average the average. So then if this is true, your result will be 0. So after, even if you multiply whatever x or divide by whatever x, still your expectation will be 0. That's the meaning of this slide. as I said, that's all you want. I want you to know. So in the end, it's unbiased. That's what we want. So your OLS estimator is an unbiased estimator for beta 1 that is coming from this assumption, right? And the next, we would like to calculate the variance. Calculating the variance is a little bit more involved, which I will ignore. I don't even the result is more complicated, but you don't need to worry about this. Just don't worry too much about this. I'll just tell you the point. First, it depends on sample size n, inversely proportional to the sample size, which is natural because as the sample size increases, if you have more observations, then your estimator will be better, obviously better. So your variance of your estimator will be smaller, which means your estimator will be more accurate, more reliable, and there will be less error. So large sample size implies smaller variance, so it's natural. And also the error term is inside here. So variance of the error term is another key determinant of the accuracy of your estimator. So as I said, if your error term has larger variance, your estimator will be inaccurate, will have large variations. And also what's interesting here is the denominator. Denominator is where is it? Denominator is this guy. Denominator is, you can think it as the variance of x. This is the variance of student to teacher ratio. So the more variation student to teacher ratio variable has, the better you can estimate. That is really something weird. You may not accept it, so it's not easy to understand. And even many like higher level students do not have this intuition. Let me try. I will explain what's going on here. Oh, I'm sorry. That's coming later. So I have to talk about something else first. So then the point here is, as the variance is proportional to 1 over n, inversely proportional to the sample size, which means the variance converges to 0 in the end. So in the limit, the variance will be close to 0, right? And however, the mean, the expected value of the estimator is always beta 1, no matter what the sample size is. So as sample size increases, variance goes to 0, but the mean, the center, does not change. So then we say beta 1 hat is consistent for beta 1, or converges in probability to beta 1. I explained this in the review slide, and the idea is when variance equals to 0, that means there is no uncertainty. And as you can see, the variance converges to 0, so your estimator will be like very accurate in the end without any uncertainty. Your estimator will be certainly correct at beta 1. So that's what you can get here. And also we are going to use the center limit theorem. Center limit theorem implies that something is approximately normal distribution with something like this, right? The center limit theorem can be stated in many different forms using different types of normalizations, standardizations. But anyhow, in the end, this is what we get. This is, so ignore what this is. Anyhow, this is what we get. Beta hat, your estimator will be normally distributed, centered around the true parameter. So which is nice. It is not, so on average your estimator is correct. It is neither overestimating nor underestimating. So the center is correctly distributed. The sampling distribution is correctly centered at the true parameter. And the variance is, again, complicated. But the point here is sample size in the denominator. Sample size in the denominator. So variance goes to 0 as you have more samples, more observations, so that you can utilize more information for your estimation. So, mathematics, and this is what I wanted to say earlier. So this part is okay. Okay, you can easily understand why n is in the denominator. Also, you can understand it is easy to see why the error term is inside of the variance in the numerator. So it's proportional. Variance of your estimator's accuracy depends on the variance in the error term. But why the variance of x is in the denominator? This is somewhat counterintuitive, possibly, but think about this. A very interesting figure. So suppose that whole data is your data, but you split the data into three groups. Actually, two groups. Blue group is in the middle, and black is on the sides. So even though I said outliers are bad, but having too small variation is also bad. So I will show you why it matters by considering two different types of groups. So the number of black and blue dots is the same. So there, I don't know how many, but the number of blue dots equals to the number of black dots. Then if you use the blue or if you use the black, basically you are using the same amount of information, but let's see how much it changes. Suppose that this is a true line. So it's just I drew it, so just conceptually, suppose that that's the true line you are going to get when you have the full data. But imagine how you are going to draw the line when you have blue. If you only observe blue observations, I think you are likely to have a line like this, right? You can see the pattern. It looks more like a very steep trend going through the dots. But when you use black, I guess it's something like this. So the point here is, of course, the lines are can be wrong. I did not have the numbers, but conceptually what I want to say here is small, because of the smaller variation for the blue dots, it is very unstable. Because the base is small, it can tilt easily. So the blue has a huge error. So the difference, the angle between the red and blue is the error, which is really large here. But black is more stable because the base is wide. Small errors does not matter. So large base implies wide base implies you are more stable. So even if there is a small changes errors on both sides, the slope itself does not change that much. So when you have narrow base, then you have a huge tilt by small error on here, like here. So this is why having variation across x, having variation across student to teacher ratio is important. In an extreme case, if you never observe any variation, for example, suppose that all the school districts have the same student to teacher ratio, like say 20, then you will never be able to calculate the effect of increasing or decreasing the student to teacher ratio to say 19, because you never observe 19. So in that case, estimation is not possible at all. No estimation is possible. So that's an extreme case, the most extreme case where the variation is zero. So as I said, outliers are bad, but having no variation is also very bad. So you should have enough variation in X to have a stable and reliable estimator. Okay, I'm going to stop here and resume in the next one. See you.